Hello everyone and welcome to Module Comp 0003, Theory of Computation. My name is James Brotherston. I'm a reader in the Department of Computer Science here at UCL, and I'll be taking the first part of the course, which is on logic. The second part of the course, which is on formal languages and automata, will be taught by my colleague Yuzuku Nakamura. So in this first lecture, rather than kind of give a lot of technical details of things you're going to have to learn straight away, there'll be plenty of that soon, but actually I wanted to give you a little bit of a sort of historical overview of some major developments in logic, try and give you some kind of a feel for why it is that logic might be connected to computation, maybe talk about some like cool results that connect logic and computer science, and hopefully give you some kind of a reason to get interested in it too. So without further ado, I think we'll look at the slides. We might come back to me in a little bit, but for now, I think definitely slides. So let's go and take a look. Okay, so let's start by asking, what is the logic? Well, at least the way I understand it anyway, it is essentially a language for formalizing arguments. And logic really has three major components. The first two of which are common to any language, such as mathematics or English. First of all, we have a syntax explaining what does and does not count as a well-formed formula in the language. Just in the same way that mathematics has a syntax, some things are proper formulas and some aren't. And just as in English, we have, some sequences of words are well-formed sentences and some are not. Next, we also have a semantics. Of course, a formula or a sentence is, in some sense, just a sequence of symbols written down on a piece of paper. Semantics is basically explains how to read the formulas of a logic, and that's usually relative to some chosen domain of discourse, or if you like, a universe. So we might think that all the formulas refer to mathematical objects such as triangles or something like that, or they might refer to computer programs, or they might refer to people and objects in the real world. Lastly, and more or less uniquely to logic, there's also a concept of inference. Of course, logic is about arguments. So in logic, we have so-called inference rules, which explain how to draw valid conclusions from a given collection of premises. Premises being kind of given facts or assumptions. You could think of assumptions as being a little bit like axioms in mathematics. In this course, we're going to concentrate on the first two of these. So really, what is a formula and how should we understand it correctly? Inference, although we'll touch on it, is going to be covered more detail in a second year module, which is also on logic. Okay, so let's go back and look at some history. And I think the origins of logic, at least the way we understand it now, are really with the ancient Greeks, and in particular with this guy here, with the reproduced in bust form. He's Aristotle. He's a very well-known ancient Greek philosopher and early logician. He pretty much laid down a lot of the foundations of what we now understand as classical logic. And all the kind of Aristotelian logic, as it is kind of now known, was all based on special argument forms which were called syllogisms. And here's one such syllogism. We have two premises, or assumptions, and then one conclusion which is drawn from that premise. So the first premise is that all men are mortal. The second premise is that Socrates is a man. And given both those two things, the conclusion is, therefore, Socrates is mortal. If all men are mortal and Socrates is a man, then in fact he must also inherit the property of being mortal. Now, in this course, you're of course not going to be expected to learn Aristotelian syllogisms or anything like that, but there are kind of two really major classical principles, which you may as well think of as laws, that go all the way back to Aristotle. And these are the following ones. Firstly, the so-called law of non-contradiction. Two directly contradictory statements so cannot be true at the same time. So for any statement, let us say A, it cannot be the case that both A and not A are simultaneously true. So if I just go here, this symbol here, the turnstile means the following thing is a law. This symbol here is a negation symbol, and it should be read as not. And then this symbol here, the kind of wedge, should be read as and. So this formula here is A and not A, which is placed in brackets. And then this whole formula is not A and not A. It's not the case that A and not A. So it's worth saying that this principle is not accepted in every logic. However, it is a fundamental principle in all of the logics that we will be studying in this course. And the second law, which is likewise a fundamental classical law, although it's not accepted by all logicians in all logics, is that every statement is either true or false. So here, this symbol, the V, means or. So it is a law that either A or not A, and that is for any statement A. I'll also say that a logic is so-called inconsistent if, using the kind of inferences of the logic, you can prove both A and not A for some statement A. So we say that it's inconsistent because somehow starting from the same point we've managed to deduce a statement and its exact opposite. Maybe I should make a few remarks about these two laws, because I mean most people I think find them quite easy to accept. If you kind of find yourself in a position where you kind of make some statement and you say, oh, it is both true and false, or it's kind of true. Well, so for example, you could look out the window and say, well, it's raining and it's also not raining. You know, it's only raining like a little bit or something. Well, I mean, in that case, I mean, it's simply the case that you just haven't made your statement precise enough. I mean, if you'd said something about if instead of it's raining, you're making a more precise statement about the exact volume of water which is falling from the sky over a sort of specific period of time, then it's a definite statement and it's either true or false. It's also kind of worth thinking about cases where we don't know whether the statement A is true or false, but nevertheless we can sort of say that it must be one or the other. So for example, you'll remember the idea of prime numbers, of course, which are only divisible by 1 and themselves and by no other numbers. And it's quite easy to prove that there are infinitely many prime numbers. But one thing that we don't know, at least the last time I checked, is you can find lots of pairs of prime numbers which differ by exactly 2. So, for example, 9 and 11, or 17 and 19. And what we don't know is whether or not there are infinitely many of these pairs of primes that are 2 apart. And this is called the twin prime conjecture. So, there may be some point at which they run out. Most people think not. But we are sure that, I mean, for sure, either there are infinitely many twin primes or there aren't. I mean, there's either infinitely many or only finitely many that run out at some point. Even though you might be skeptical as to which one, and maybe we will never know, it surely must be one or the other. Or we could also think about the statement A, which is UK Prime Minister Boris Johnson has exactly 7 children. Now, I would say that probably not very many people know whether that statement is true or false. Perhaps even UK Prime Minister Boris Johnson doesn't know whether it's true or false. But for sure, he either has exactly 7 children or he doesn't, in which, he has fewer or more children than that. So even though it's not accepted in kind of all logics, where sometimes we admit ideas of statements somehow being both true and false, or neither true nor false, or some kind of fuzzy logic where statements have a truth value which is somehow in between true and false. But that's not going to be the case here. Every statement is either true or false by the law of excluded middle, and never both by the law of non-contradiction. And funny enough, that was really about it for about 2,000 years. Logic was considered to be, barring a few minor developments, pretty much set in stone for a long time after that, until people started to take more interest in it in the 19th century. So this guy here is Gottlob Frege, this guy in the picture here. He was a Victorian era gentleman, and he lived in Germany, and he developed what's called predicate logic. You can just remark on his rather fine beard there. I think that's a beard that we can all be proud of. I mean, its sheer kind of sprawl is quite impressive, especially when kind of juxtaposed with his incredibly neat hair. I mean, so it's obviously a deliberate effect. Anyway, enough about the beard, and more on to the logic aspects. Okay, so he developed what is called predicate logic, which is still adhering to Aristotelian principles, but is somehow now becoming into more of a symbolic form, which is more akin to what we use today. So here I've written down some form of the previous Aristotelian syllogism, but using the language of so-called predicate logic. So let's take a look. The first line, the first premise, is a translation of the statement "all men are mortal." So this upside down A should be read as "for all" and X. So this here means for all X, and then we have the formula man of X. So man is what is called a predicate, or it's a property of objects. So man of X stands for X is a man. And similarly, mortal here is another predicate or property of things. So for all, and the arrow means implies, or so A arrow B means if A then B. So this first line says, for all X, if X is a man, then X is mortal. And that's a translation of all men are mortal. And the second premise is Socrates is a man. So here we're saying that we have some object or a constant, Socrates, which represents something in the universe, in this case, the man Socrates. And this premise says that actually Socrates is a man. We have man of Socrates. So that's the second premise. So now we can have, we can think of specializing the first premise, since for all X, if man of X, then mortal X, then in particular, it must, I mean, anything that is true for all X must be true of any particular X that you can think of. In particular, it must be true of Socrates. So since for all X, if man X, then mortal X, then it must be the case that if man Socrates, then mortal Socrates. So that comes just from the first line. And now we can say we have we now have two facts that are relevant. One is that Socrates is a man, and the second is that if Socrates is a man, then Socrates is mortal. Now, we have the kind of principle that if you have A, and you have if A then B, well then you must have B, because that's really what the meaning of the word if is. So since we have man Socrates and if man Socrates then mortal Socrates, then we must obtain mortal of Socrates. So this here is the conclusion of the original syllogism, that Socrates is mortal. And we have here like an intermediate step where we've made like a sort of an intermediate inference. Now, at this point, I think it's useful to kind of go back and just kind of think about these predicates. So I said that a predicate was a property of objects, and by a property of object, you can think of that as being essentially the same thing as the set of all objects having that property. I mean, if you think what a property really is, you can kind of think of it as either somehow you can think of it as a function which takes objects and answers yes or no, according to whether an object has that property or not. Or you could just think about forming the set of all things that does have that property and checking whether it's in the set. So for that reason, set theory is very kind of relevant to logic here. And I wanted to just kind of go back and talk about it. I'm sure that most students will know quite a bit about set theory already, and you should have learned some in the discrete mathematics course. But I think it's better just to go over a few things just so that we're all on the same page. So naively, set theory says, well, for any property we can think of, we can form the set of objects that have that property. So a set for that reason could be finite. We could think about the set of all humans on the planet Earth at the present moment named James, which is definitely a finite set. Or we could think of an infinite set, such as the set of all prime numbers, and that's definitely an infinite set where being prime is a property of numbers. So if I want to denote the set of objects having the property P, I'll usually write it in this kind of set notation here. So we have the set brackets to denote that it's a set, and we have the set of all objects X such that, that's this bar here, property P holds of object X, so that all X such that P of X. So that's the set of all objects X having property P. We also have this notation here, X in Y, and that so where where Y is a set, big Y is a set, and little x is an object, and that notation means that the object X is a member of the set Y. Oh, sorry. And we also have this notation, X is a subset of Y. So this symbol here means is a subset of, so it means set X is a subset of set Y. So X and Y are both sets. I'm usually writing capital letters for sets and small letters for objects. So when I say that set X is a subset of set Y, I mean everything in X is also in Y. Every object in X is also an object in Y. So it also means that X and Y could be equal, as a matter of fact. But for sure, at least X is contained in Y. That's what that means. And in fact, I mean, set theory is super useful. In particular, it can describe virtually all of mathematics. So super useful. Let's see some examples of sets. So this object here, this kind of zero with a stroke through it, is notation for the empty set. The empty set is the set containing no objects. Here we have a set of 4 objects, A, B, C, and D. So that's a finite set containing 4 objects. We also have here the set of natural numbers, which is often written using this blackboard style N. That's notation for the natural numbers. In computer science, we usually count the natural numbers as starting from 0 rather than 1. So that is all the numbers 0, 1, 2, 3, 4, and so on. That is, of course, an infinite set because there are infinitely many natural numbers. Next, so here I'm picking out a subset of the natural numbers. So I'm saying this is the set of all objects n in the set big N. So all natural numbers n, little n, such that little n is greater than 3. So that's everything in the set n having the property of being greater than 3. So that is all the natural numbers 4, 5, 6, 7, 8, 9, and so on. That's also an infinite set. It's an infinite subset of the natural numbers. Here's another example, which I mentioned before. All the natural numbers n such that n is prime. And here, actually, we usually don't count 1 as being a prime number, so that's my mistake there, sorry. So maybe ignore number 1. But this set contains all the numbers 2, 3, 5, 7, 11, 13, 17, 19, and so on and so forth. So that also is an infinite set, again, an infinite subset of the natural numbers. Here's a more complicated thing. So we can also form sets of sets. So this is the set of all sets x, such that x is a subset of the natural numbers. Okay, so what is a subset of the natural numbers? Well, the empty set is definitely a subset of the natural numbers. So the empty set is a member of this set. The set containing just one number, 0, is a member of the set because it's definitely a subset of the natural numbers. Likewise, the set containing just the number 1, just the number 2. So we have all the 1-element subsets of the natural numbers. And then we also have all the 2-element subsets of the natural numbers. So 0, 1, 0, 2. And it would also contain things like 101 and 17 and so on. And then, of course, we'd also have all the 3-element subsets, all the 4-element subsets. And in fact, we would have infinite subsets as well. So both of these two sets above are subsets of the natural numbers. So these two subsets both belong to this guy down here as well. So that's a pretty big set of subsets of natural numbers. Now, exactly how does this connect to logic? Well, supposing that I define two sets in the following way, and they're going to kind of correspond to my predicates of being of man and mortal. So for y, I'm going to write the set of all x such that x is a man, and set z is all x such that x is mortal. So then, if I want to write down the previous Aristotelian syllogism, which is all men are mortal, Socrates is a man, therefore Socrates is mortal, I can write it down in the following way. To say that all men are mortal is to say that everything that is a man is also mortal, which is a way of saying that that really every object in the set Y, which is all the objects that are men, is also an object in set Z, which is all the objects that are mortal. So, some other things may be mortal that are not men, for cats and dogs and piggies and that kind of thing. But I can write down the statement all men are mortal just by saying that set Y is a subset of set Z. All men are mortal, Y is a subset of Z. So, easy enough. But then the second premise is even easier. I say Socrates is a man. Well, another way of saying that is to say that Socrates is a member of the set Y. Among the objects that are in Y are included Socrates. So Socrates is a man. If Socrates is a member of Y, then by definition, Socrates is a man. And therefore, Socrates is mortal. Therefore, Socrates is a member of Z. By the same reasoning, to say that Socrates is mortal is exactly the same as saying that Socrates is a member of the set Z. So there's a very close connection between predicate logic and sets. And in fact, when we come to examine the semantics of predicate logic later in the course, then we're going to critically rely on set theory in order to understand the meaning of formulas. Hello again. So at this point, I think there's something which is really interesting to think about. Something interesting to think about is there such a thing as the set of all sets? Well, naive set theory would say yes. Remember that naive set theory says for any property that we can think of, we can form the set of objects having that property. Well, being a set is certainly a property, and there's no problem in forming a set that contains other sets, as we've already seen. So yes, being a set is a property, so we can form the set of all objects having that property, which was the set of all sets. So, okay, but actually it turns out that this breaks everything. Having a set of all sets is a bit like being that one annoying kid when you're playing superheroes that says, well, my power is having all the powers. Turns out that it kind of breaks everything. We'll see why exactly in a moment, but first let's make a few sort of preliminary observations. First of all, let's ask the following question. Does the set of all sets belong to itself? Is it a member of itself? Well, yes. Yes, it's a set, and therefore it must belong to the set of all sets. So the set of all sets is a member of itself. Okay, so then let's go a step further. Can we form the set of all sets that are members of themselves? Again, yes. Let me see. The set of all sets belongs to itself. So that's an example of something that has the property of belonging to itself. And we can also think of sets that don't have the property. So, for example, the set containing the numbers 1 and 2. It's only got 2 numbers in it. Numbers are not sets. So it definitely cannot belong to itself. So it seems like a sensible enough property. It's the property of being a set and being a member of itself. Some sets belong to it and some sets don't. And now, I suppose, since we can think of the property of a set belonging to itself, we can also think of the property of a set not belonging to itself. So we can also think about the set of all sets that are not members of themselves. And as soon as we do this, as we shall see in just a moment, everything breaks and we encounter what we mathematicians like to call an oh shit moment. Oh shit. Let's see why. Okay, so here's our next famous figure. This is Bertrand Russell, who's an English philosopher and mathematician from England. He lived here in London for some time. I think you can go and see his house. And a fairly early point in his life, in 1901, when he was not yet 30 years old, he said, consider the set of all sets that do not contain themselves. So I already explained in my little segment before why this seems like a perfectly reasonable set to kind of consider. So this set I'm calling R, the set of all sets X, such that X is not a member of X. So remember that, for example, some members of R would include things like the finite set consisting of numbers 1 and 2. That is definitely not a member of itself, and therefore it belongs to R. And then we can also think of the set of all sets. Well, that is definitely a member of itself, and therefore it does not belong to R. However, what about the following question? Does R belong to itself? Now, if R is a member of R, then by definition, since the only things in R are things that are not members of themselves, then R is not a member of R. So it both is and is not a member of R. And that's a contradiction. And remember, our law of non-contradiction says that is impossible. Since it's impossible, we conclude that, well, that's where we get to if we suppose that R was a member of itself. So it obviously can't be a member of itself. But then R is not a member of itself, which means that by definition of R, it actually is. R is the set of all things that are not members of themselves. If R is not a member of itself, then it must be a member of R. So again, we have a contradiction. This is called Russell's paradox, which means that basically, no matter whether R is or is not a member of R, and remember that we have our law of excluded middle saying that it must be one or the other, then it has to be both in R and not in R. And remember, our law of non-contradiction says that's impossible. This shows that naive set theory is actually inconsistent, since it allows us to form the set of all sets, and therefore this particular set R of sets that don't contain themselves. And so the problem really, if we want to analyze the problem was in allowing ourselves to sort of do something quite so naive as constructing the set of all sets, which is a bit like having a bit like the superpower of having all the superpowers. It's too much. So this, it really alarmed a lot of mathematicians at the time, and rightly so, because a lot of mathematics is based on set theory, as I said, and oh shit, we've just shown that the kind of set theory that everybody uses can allow you to derive contradictions. So, if this part is wrong, how much else has gone wrong? Oh my God. Fortunately, it didn't have quite such a practical impact as might have been supposed. Because it turns out that most of set theory, the part of set theory that is most commonly used in practice in mathematics, actually is consistent. Most people don't go as far as employing things like the set of all sets or similar kind of constructions. But, you have to do some work in showing that. So people put a lot of effort into constructing non-naive versions of set theory, saying, exactly how it is you're allowed to build up sets from, you kind of say, what are the smallest allowable sets? So, finite sets are basically okay, and the empty set is okay. And then you can kind of build up larger sets from these, including infinite ones. But you have to be quite careful about it. It was definitely an area where, logic, which had not until then been sort of considered to be of much import to mathematics, actually showed that a large part of mathematics itself was potentially inconsistent and would have to be considered very, very carefully. And it also kind of set off a bit of an investigation in mathematics in the early 20th century as to, well, okay, actually, which parts of mathematics can we show are consistent in that they don't contain any implicit contradictions? So here we have our next figure, David Hilbert, who's an early 20th century mathematician, or at least his most famous work, I think, was done in the early 20th century. And in 1920, he launched a grand program, a grand scheme, aiming to find some kind of logical system for all of mathematics, so some set of like axioms and proof rules that was at the same time, number one, consistent in that no contradiction should be provable in the system, and secondly, complete. Complete in the sense that every true statement in the logic should be provable. So it's an entirely laudable aim, and one that was unfortunately turned on its head by kind of mathematical logic's second and perhaps greatest oh shit moment. So here, this guy, we have Kurt Gödel, author of the Gödel completeness theorem, and then more famously his incompleteness theorem. So his incompleteness theorem showed that any logical system which is powerful enough to at least include standard arithmetic over the natural numbers, so by standard arithmetic I really mean it should include addition and multiplication and the principle of induction over numbers, and just those kind of basic things. So fairly basic, but at least in kind of enough to do conventional arithmetic in, must either be, number one, incomplete, meaning that there are some true statements in the system that are not provable, or else, if it is complete, then it in fact must be inconsistent, which means that a contradiction is provable. So since a system like that is either not complete or not consistent, it certainly it shows that there can't be a system like that which is both complete and consistent. And of course, this rendered the Hilbert program completely unachievable. He wanted to find a logical basis for mathematics that was both complete and consistent, Gödel's incompleteness theorem shows precisely that such an endeavor is absolutely hopeless. So, yeah, and that's a second really big oh shit moment in logic as and kind of applying to mathematics. And let's move on to our next big figure. So our next famous figure in logic is Alan Turing. And although he's really very well known these days, he's on a banknote, and they made that film about him with him off Sherlock Holmes in it, and which is complete nonsense, but never mind. But of course, he was not really well known for a long time before that, except really to computer scientists. I mean, he is regarded as one of the kind of fathers of computer science in many ways, and in particular for his development of a model of computation which is known as the Turing machine, which he came up with sort of in the mid-1930s. You will meet Turing machines in much more detail in the second half of this module and in future courses, I believe. But I think the first thing to remember is that in the mid-1930s there was really no such thing as computers in the sense of machines as we know them today. Rather, a computer was not a machine but a job. It was like a job that people could do. And really, the way to think about it is that if you give a computer, meaning a person, an exercise book and a pen and a set of instructions for carrying out a computation, then they don't really need to think. They just need to perform the computation according to the instructions that they've been given. And of course, they can perform different computations given different sets of instructions, which was quite a sort of a novel concept at the time. The idea of having a stored program computer, which could be given different sets of instructions. So if you think that, for example, you asked me to calculate the base 2 logarithm of 10,000 or something like that, well, as long as I had paper and pen and a set of instructions for calculating the base 2 logarithm of a number, then I wouldn't have to think. I would just have to carry out the instructions. So in the Turing machine model of computation, the exercise book, or the computer memory, if you want to think about it that way, is replaced by a kind of a tape, which is divided up into kind of squares. The squares being like squares on the exercise book or something like that. So, or, individual locations in the memory, if you want. And the idea is that the Turing machine also has a head which can examine one square of the tape at any given time, and the tape itself contains symbols which might be blank, or there might be alphanumeric, or even you could think about doing it all in binary, and so it just contains zeros and ones, which is again very like the sort of very like how things are done now. So some numbers there, and at each stage of the computation, the Turing machine can do one of a very limited number of things depending on which step of the instructions it's at, which is kind of its internal state, and what number it is looking at or what symbol it's reading on the tape. It can either go left 1 square, or it can go right 1 square, or it can overwrite the symbol that it's reading at the moment with another symbol. And those are the only 3 things that it can do. Surprisingly enough, this model of computation is actually powerful enough to describe anything that we can think of as computation today. So no matter how powerful your computer or mobile phone, or no matter whether you're thinking about doing functional programming or concurrent programming or object-oriented programming or anything, it turns out that it can all be described in terms of a sufficiently complicated Turing machine. And whenever anybody has ever proposed an alternative model of computation, and many people have given alternative models over the years, they have always turned out to be exactly equivalent to each other. So in fact, we even have this very often now when we say computable, sometimes people also say Turing computable, meaning computable by a Turing machine. But in fact, we might as well just say computable because we don't really know how to compute anything that is not already computable by a Turing machine. Amazing. Let's go back to the slides. Okay, so this slide just recaps what we went through in the last segment. So here's Alan Turing, looking very neatly groomed here. And he invented the Turing machines, which we described also in the last segment, that can describe all known computation. And he proved one of the most famous results in computer science, which can be described in the following way. It would be super useful to have a program that can decide whether any other program halts. So we would give, we would give that program another program as input, and it would tell you whether or not that program is going to halt or not. So this is called the halting problem. Given a program P, we can think of a program as being a Turing machine, and an input I, which is a kind of an initial tape contents. Decide whether the program P halts when run on input I. Now, Turing famously showed, using logic, that this problem is undecidable. By undecidable, we mean there is no algorithm or no program that decides the problem, which is to say, answers correctly and terminates on all inputs. So the flavor is actually quite similar to the Russell paradox, which we showed before. You suppose that you had a decider program for the halting problem, so a program that can decide whether any program terminates on any input, and then you use that program to build another program which halts even only if it does not halt. And of course, if it halts, then it does not halt, it loops forever. And if it loops forever, then it must halt by construction. And again, that's a contradiction. And the conclusion is that the halting decider program can't exist in the first place. So in fact, there is no general algorithm for deciding whether programs terminate on a given input. Which is not to say that we can't decide whether at least some programs terminate, and that we do have automatic methods for at least telling whether programs terminate some of the time for some small classes of programs and this kind of thing. But there's no general way of doing it. And so this is a really fundamental result in computer science. And later on, it was actually extended by somebody whose second name is Rice. There's a theorem known as Rice's theorem that says that practically any non-trivial property of programs, such as, will X ever become equal to 0 or something like that, where X is like a program variable, all of those properties are undecidable as well. So while you can prove it in some cases for some programs, there's no way of deciding it automatically for every program. Okay, so here's our last famous figure of the lecture, who's Tony Hoare. Unlike the other figures that we've discussed so far in the lecture, Tony Hoare is still alive. He works for Microsoft, although I think he must be by now mostly retired, but I think he is still active. I mean, I've met him once or twice at conferences. I have heard of decolonizing the curriculum, by the way. I should say that there are, of course, many female and non-white logicians and computer scientists working today. It just so happens that the early history of logic and computer science is quite white man heavy for the usual kind of racist and sexist historical reasons. So Tony Hoare is probably his most fundamental, or one of his really big contributions to logic and computer science, was his proposal for showing that programs were correct. Of course, by Turing's results, this is not decidable most of the time, but you can, for particular programs, attempt to construct a mathematical or a mathematical logical proof of their correctness. So in 1969, he proposed a kind of logic for reasoning about the correctness of computer programs, and that's based on these Hoare triples here. So the format is A, C, B. Those brackets, they look like set brackets, but they mean something different here. So C is a program that goes in the middle, and A and B are logical formulas that describe the state of the memory, the computer memory, before and after the computation of C, respectively. So the formula A is often called the precondition, and it describes the memory state before you start the program. And the formula B is often called the postcondition, and it describes the memory state after execution of C. So typically, A and B might, for example, describe numerical constraints on the program variables, supposing that the program is doing something arithmetical. So for example, if X and Y are program variables, then an example might be X is equal to 1 and Y is less than 2. That might describe the state of the memory before computation or after computation. Doesn't make much difference in this particular case. And the way you read those triples, A, C, B, means that whenever you run the program C in a memory state that satisfies the formula A, so that in other words, the formula A is true of the initial memory state, then if it terminates, its final memory state satisfies B, meaning B must be true of the final memory when it finishes. So we can give rules for these Hoare triples, and so we can use this to construct a logical proof, just like a proof in geometry or algebra or any other, or indeed in mathematical logic, that a particular program C has a particular property or satisfies a particular Hoare triple. And this is what we can call program verification, which is really means that mathematically proving that a program does what we want it to do. It's not always very practical to do this for programs that are more than just a very small size. I mean, if you think, and the reason, one of the fundamental reasons is that constructing proofs is difficult. Think about constructing a proof by induction. You have to guess an induction hypothesis, and we'll definitely examine that later in this part of the module. But also, the proof might be quite a lot larger than the program in general. In fact, I mean, it usually is. And if you think that that even if the proof is only quadratic in the size of the program, but the program is 1 million lines long, then it means that the proof might be 1 million lines long. And so that is definitely a problem. But some recent advances have made it possible to do this for very large programs. And it really takes advantage of a principle known as compositionality, where if you have a program with 1,000 procedures, the kind of all you really need to do is verify each one of those procedures individually, and you don't have to worry about how they all interact together. So compositional really means that the correctness of the result only really depends on the correctness of the individual components. So one example of this is the Facebook Infer Verifier. So you can look this up. It's open source software, and it's based on mathematical logic principles that were partly developed here at UCL by my own boss, and I've kind of worked on it myself. And before that, when they were at Queen Mary. It uses something called separation logic, which is a particular kind of Hoare logic that is very good for dealing with memory. And now what happens when you run Infer is that Facebook are developing a new version of their mobile app, or new versions of their server code, and we have developers putting in commits all the time. And every time they put in commit, then the infer verifier tries to automatically construct a proof that the new code is memory safe, so it doesn't contain any pointer dereference errors or anything like that. And if it can't prove it, then it sends a warning automatically to the developers, who can then sort of treat it as a bug report. So just to finish up, let's mention some other areas in which logic is really central to modern computer science. It's really important in databases because you use it to express the queries. You know, select all the rows that belong to this and this, but don't have that property, and so on. It's really important in hardware and circuit design. I mean, of course, if you get down to the circuit level, circuits are built out of logic gates that can correspond to logical operators, and we'll talk about that very briefly in a few lectures' time. It's really important in the design of programming languages, because in order to give programming languages, we have to give a semantics really to kind of say what the various constructs of the language are actually supposed to do, and to and to show exactly how this works. Then logic is really key, a really key tool in there as well. It's also very important in machine learning and artificial intelligence. So, I mean, although of course I would say this, and of course you have to learn logic for this course, no matter whether you want to or not, my contention is that logic is really useful. It's really interesting. Of course you have to learn some, but I also think you should learn some, and I really hope that you enjoy learning a little bit in this course. Okay, well, that's pretty much it for this lecture. I hope you enjoyed it. Thank you for listening, and I will see you again in lecture 2, where we're going to start looking at propositional logic. Until next time, take care.